Hello, chemistry. Welcome back to online lectures. We're going to talk about covalent bonding today, but before we jump into covalent bonding, let's do a little bit of review about a couple of these topics. So first of all, this is the third type of bonding we have talked about. We talked about ionic compounds, and we talked about bases within that because bases are ionic compounds. We've talked about metallic bonding. And now this is our third type of bonding we're going to talk about, which is covalent bonding. So covalent bonding happens for a different reason. Uh, we predict the formula in a different way, and we also name it in a different way. So covalent bonding is its own system, and we want to talk through a couple parts of that system right now. We're not going to talk about all of it. We'll do it kind of piece by piece, but let's introduce ourselves to this idea of covalent bonding. So before we jump into that, I want to review Lewis dot diagrams and electronegativity. So remember, with Lewis dot diagrams, this is a representation of the valence electrons. And the valence electrons only. Now, we did talk about another system that represents all electrons, which is the Bohr model. So in the Bohr model, we would look at carbon on a periodic table, and we would see that carbon has 6 protons, and therefore a neutral atom of carbon also has 6 electrons. So in the Bohr model, we would represent all 6 of those electrons, right? The first 2 go in the inner shell. That's the 1s shell. And then the next 4 go on the second shell. So that would be the 2s and 2p suborbitals, or the second shell holds 4 total. The first shell holds 2. And the second shell for carbon holds 8. So that would be our Bohr model. Now, that's a really good way to represent electrons. It helps us to understand a lot of different things, but sometimes we only need to deal with the valence electrons, like in bonding. In bonding, those core electrons on the inside are not involved in bonding. Only the 4 on the outside are involved in bonding. So we want a way to represent just the valence electrons, and that for us is going to be the Lewis dot diagram. So you have to figure out how many valence electrons you have. That can be done by looking at the electron configuration. That can also be done by looking at a periodic table. Because remember, each of the families has the same number of valence electrons. So the first family, the alkali metals, has 1 valence electron. The second family, the alkaline earth metals, has 2 valence electrons. The third family has 3, and the fourth family, which is the carbon family, they all have 4 valence electrons. And so we can just count over the families of the representative elements and also figure out how many valence electrons an atom has. So carbon has 4 valence electrons. Now we want to represent that around the symbol. So notice that there's a symbol here for carbon. And then we're going to represent those 4 valence electrons. So when we do that, we're going to draw them as if they exist on the sides of a box. So we have 4 sides on which we can put electrons, and then we are going to spread them out until we are forced to pair them. So we put 1 valence electron, 2 valence electrons, 3 valence electrons, and 4 valence electrons around carbon. Now, I don't have to pair any of them. They all can exist on their sides unpaired. So that is the Lewis dot diagram for carbon. Why don't you pause the video here and try the Lewis dot diagram for chlorine and also for sodium. So with sodium, we know it's in the first metal. Sodium is an alkali metal, so it's only going to have one valence electron. And so I'm just going to put that one valence electron on one of the sides of sodium. Chlorine, on the other hand, is a halogen. Oops, that's actually probably where fluorine is. Chlorine's more like there. So chlorine's a halogen. Halogens all have 7 valence electrons. So I'm going to put 1, 2, 3, 4 valence electron. Now the 5th valence electron is going to pair. So 5, 6, and 7. So that's what chlorine is going to look like. Chlorine is going to have 3 pairs of electrons and then 1 electron that is unpaired on the side. All right, so we talked about that before. We've practiced that before. That is Lewis dot diagrams for atoms. Now we're going to build on that moving forward with covalent bonding in just a minute. So put that in your back pocket and let's talk about electronegativity. Okay, so electronegativity is one of our periodic trends. And remember, electronegativity is the energy of attraction, right? So it's how much the nucleus can attract a valence electron. We talked about this in terms of force of attraction when we did our Coulomb's law Pogel packet. That would be a good one to go back and review. And we saw that force of attraction was proportional to the nuclear charge. So as nuclear charge went up, force of attraction went up. And it's indirectly proportional to distance, actually distance squared. So as distance goes up, the force of attraction goes down. Okay, so electronegativity is one of those things where you should be able to look at a periodic table and tell me which elements are more electronegative and which elements are less electronegative. And this is actually one of the driving factors of covalent bonding. So if we look at a periodic table again, all right, as we go left to right in a row on a periodic table, we can take the second row, for example. As we go from the left to the right, the nuclear charge is going to increase. Lithium has 3 protons, beryllium has 4, boron has 5, carbon has 6, and so on and so forth. So as we go from the left to the right on a periodic table, we're going to increase in nuclear charge. And our distance doesn't change. Remember, that's an increase in our nuclear charge, while the electrons in that second row all sit in the second energy level. So there's no increase in distance. There's only an increase in nuclear charge, and therefore electronegativity is going to increase. In class, we drew it like this. Right? So if we compare like lithium to fluorine, for example, lithium has less of a nuclear charge and therefore it will have less electronegativity than fluorine. When we go top to bottom in a periodic table, the nuclear charge is increasing, but the distance is also increasing. Like hydrogen has 1 energy level, lithium has 2 energy levels, sodium has 3 energy levels. And so the valence electron that's in that outermost ring is going to be farther and farther and farther away from the nucleus as we go down that family. Now, which factor plays a more important role? That would be distance. Distance is related to the force of attraction through a square. Nuclear charge is not. And so as distance increases, it kind of rules over nuclear charge. So the things on the bottom of that row are going like francium are going to have a smaller electronegativity. As we go top to bottom, electronegativity is going to decrease, and we drew the little arrow like this. So if we were comparing lithium to francium in terms of electronegativity, lithium would be more electronegative than francium. Okay, so here's where this becomes important. When we start to look at elements that are bonding with each other, we can predict what type of bond they're going to form by looking at their difference in electronegativity. Let me clear this a second and we'll look at a couple pairs. Okay, so sodium and chlorine, for example. Let's redraw that periodic table so we kind of have a ballpark. So this is a really good thing to do with a periodic table in front of you. As we go through this, you should be pausing the video and finding these elements so you can see where they are on a periodic table. Now, I've dealt with elements enough that I can just tell you where they are on a periodic table, but you should never be trying to predict bonding or electronegativity or Lewis dot diagrams for that matter without a periodic table in front of you. As you do your chemistry notes, your chemistry homework, you should always have a periodic table in front of you. All of this information is contained there. And as you use it, it's going to become easier and easier to use. You're going to become more and more skilled at using a periodic table. Okay, so let's find sodium and chlorine on a periodic table. Sodium is going to be about here. Chlorine's going to be about here. So let's talk about their difference in electronegativity. Are they going to have a very high difference in electronegativity? Are they going to have a very low difference in electronegativity? And sodium and chlorine are going to have a very high difference in electronegativity. They are almost as far away from each other on the periodic table as you can get them. And so they'll have an extreme difference. Because of this extreme difference in electronegativity, sodium has very low electronegativity. There is not very much attraction between sodium's nucleus and its electron. And so sodium is going to tend to let that electron go very easily. Doesn't take a whole lot of energy to pull it off. Chlorine, on the other hand, has a very high electronegativity. And so chlorine is going to hang on to its electrons very strongly, and it's going to grab any electrons that are near it very strongly as well. And so when this happens, when sodium doesn't really have a hold on its electrons and chlorine's trying to gather as many electrons as it possibly can, we get an ionic bond. An ionic bond is going to have a very high difference in electronegativity. And so sodium is going to tend to give its electron up and chlorine is going to take it. So if we were going to draw a Lewis dot diagram for an ionic compound, it would look something like this. Chlorine now has a negative charge. Sodium now has a positive charge, and there's an arrow showing the transfer of electrons. Okay, so very high electronegativity differences are going to result in a transfer of electrons, and that's what we call an ionic bond. It results in a transfer of electrons. It results in ions or charged things within the lattice, and that's an ionic bond. Let's go to the other side of the spectrum here, and let's look at the chlorine-chlorine difference in electronegativity. So if we look at chlorine compared to another chlorine, what's the difference in electronegativity there? None, right? There's no difference in electronegativity. They are the same element. They're going to have the exact same electronegativity. So what happens with their electrons? They each need an additional electron, right? Chlorine has 7, the other chlorine has 7. So they are unstable because of the octet rule, right? They each need one more. So one of the chlorines is going to be attracted to the other one's electron, and then vice versa, right? They're both highly electronegative elements. They're both actively seeking for other electrons. They're going to be attracted to each other's electrons, but they're not going to be able to pull them away because there's no difference in electronegativity, right? And so what happens is these two things become attracted to each other, but they don't actually take the electrons away from each other. So they tend to share electrons, and that's what a covalent bond is. So if you have no difference in electronegativity, you are going to form a covalent bond. And we'll talk about what the Lewis dot diagrams for those look like in just a second. But let's return to this last example here, carbon and chlorine. So carbon and chlorine, carbon's going to be about here on the periodic table. Chlorine's going to be about here. So they're kind of close together. What can you tell me about their difference in electronegativity? It's going to be small. They will have a small difference in electronegativity. So the question is, how small is it? Is it big enough so that one can steal from the electrons from the other, or is it small enough where they can't steal electrons from one another? So this is actually kind of an interesting case with carbon and chlorine. Carbon tends to be less electronegative. It doesn't have a real strong hold on its valence electrons. And we already talked about chlorine before. Chlorine has a very strong pull. It's going to try to pull electrons away. So what actually happens in this case is that chlorine is going to have an attraction for carbon's electron. It's going to pull it away a little bit, but it can't pull it away completely because carbon is still a little bit electronegative, right? So they do end up sharing electrons. It is going to be a covalent bond, but it's not the same covalent bond as the chlorine. Chlorine, here we have perfect sharing, right? Here we have unequal sharing. Chlorine does pull the electrons away from carbon a little bit, not completely, not enough to make a charge, but they do pull it away a little bit. And it actually leads us to something called a polar bond. So we're going to return, after we talk through covalent bonding, we're going to return to talk about this idea of polarity. And you can see here where this idea of polarity comes from. It comes from a small difference in electronegativity, not big enough to pull the electrons away, but it's not perfectly shared either. You may have heard of polar things already, right? You may have heard of something like water being polar. And because water is polar, it has all these different properties or things it can do. So polarity is a really important topic, and it has to do with covalent bonding. And we will return and talk about polarity in a couple days. Okay, so if we look at our chart here, from the purple to the pink to the blue, right, from a high electronegativity difference all the way down to a no electronegativity difference, the question is, well, where's the cutoff, right? Where's the cutoff between a small electronegativity difference and a big electronegativity difference. Now, if you look at electronegativity on a scale, if you look at the numbers that actually represent electronegativity, you'll see there is a number value. And above this number value, it's going to be ionic. And below this number value, it's going to be covalent, right? So we can look up that number value just so you see that it exists. But what this really comes down to is what we've always talked about. What kind of things form ionic bonding, and what kind of elements are involved in covalent bonding? You can probably answer that, right? In ionic bonding is going to be between a metal and a nonmetal. A metal and a nonmetal are going to equal an ionic bond. So why is that? It's because they have such a high difference in electronegativity. So we actually don't need the numbers. We don't need to go look up that chart of electronegativity difference, because what we can do is just kind of look at the periodic table. If you're trying to bond a metal with a nonmetal, oh, sorry, I did that backwards. No, I didn't. A metal with a nonmetal, you're going to get a really high difference in electronegativity, and that's going to be an ionic bond. If you're trying to bond a nonmetal with another nonmetal, that's going to be a really small difference in electronegativity, and so that will be a covalent bond. Whether it's a covalent bond that has a small difference in electronegativity or a covalent bond with no difference in electronegativity, they're always going to be a non-metal bond. And that's how we determine whether something is going to be ionic or covalent. But now you understand why. It all comes down to the difference in electronegativity. Okay, like I said, we can go look at that electronegativity chart. Notice that when you're looking at this chart, you see that these things actually have values, like sodium here is 0.9, chlorine here is 3.0. So if you subtract those, the difference is going to be very big. It's going to be 2.1, right? Whereas carbon here, which is a 2.5, and chlorine here, which is a 3.0, it's their difference. When you subtract those, their difference is going to be rather small, 0.5 of difference. And chlorine, that'll be a difference of 0, right? You subtract those, you get 0. So we can come down and do this in terms of numbers, but really what it comes down to is that division of the metalloids is going to divide us between a big difference in electronegativity and a small difference in electronegativity. Okay, now this leads us to a lot of different properties. We have talked about the different properties of metals and the different properties of ionic bonds. So now let's come full circle and talk about the different properties of covalent bonds. So what kind of properties does this lead us to? All right, so we have talked about a couple of this before. Here's a chart of all the different types of solids. Basically, if you're looking at solids, you are either going to have an ionic solid, a molecular solid, or an atomic solid. And then there's 3 types of atomic solids. There's a metallic, group A solid, and a network solid. Okay, so all of these 3 different types of solids come down to what is at the point in the lattice. So remember, whenever you have a solid, you have a lattice that forms. And if you look at what's actually present at the points of the lattice, you're going to see what type of solid it is. So an ionic solid is going to have ions at each point in the lattice, and that leads to distinct properties. A molecular solid will have a molecule at each point in its lattice, leading to specific properties. And then an atomic solid will have atoms at the points in its lattice, leading to specific properties. So let's kind of talk about what these properties are. We have talked about the properties of ionic solids and metallic solids already. So here's an ionic solid. This is our favorite ionic solid because we're all familiar with it and you can just go find it in your household, right? This is table salt, sodium chloride. So any ionic solid we actually call a salt. So calcium chloride would be a salt. Sodium chloride would be a salt. Calcium carbonate or chalk, we call that a salt. Anything that's an ionic solid, we're going to call a salt, right? But the one that we're all familiar with, sodium chloride, is table salt. Now, just because it's a salt doesn't mean you can eat it. So don't go try to eat all these other different types of salts. Please stick to table salt. Let's restrict our diet to sodium and chlorine, shall we? Let's do that. Okay, so we've talked about the properties of ionic solids. Can you pause the video and list them now? Properties would include a really high melting point and boiling point. So to get them to melt or to boil, you have to raise it to an extremely high temperature, right? They're going to tend to be hard and they're going to tend to be brittle. As soon as you misalign those ions in the lattice, they're going to repel and break and fracture, right? And break apart. So they're going to tend to be very brittle. We've talked about metals too and how metals have very special properties. So you can see the lattice of a metallic solid also has atoms at each point of the lattice. The one that we looked at last quarter was aluminum, and how aluminum will actually give up all of its valence electrons and form the sea of electrons. And because all these electrons are free flowing, free moving around their nuclei, which are now cations, right? Because they've given up all their valence electrons to the sea of electron. Metals tend to also have high melting points and boiling points. They are very happy in their solid state, but they get this host of other properties, like they are conductive. They have luster, also known as shininess. They are malleable and ductile. If you hit this with a hammer and these atoms misalign, the electrons are just going to shift and it's going to stay in that shape now. So metals are bendable because the sea of electron can ebb and flow, whereas ionic solids are not bendable. You misalign those ions and they fracture apart, right? And so its distinct structure is going to give rise to all of its kind of crazy properties. Now, the last couple groups, molecular solids and atomic solids, these are actually going to be our covalent structures. So if you have a molecule at each point of the lattice, like this molecule is methane, the molecule that you're seeing down here is actually sucrose or sugar, right? This is rock candy. These are molecular solids because at each point in the lattice, they're going to have a molecule. Now, that's going to give rise to very different properties than the atomic solids. So this atomic solid that you see here that has oxygen and silicon in there, that's going to be silicon dioxide, which is sand. Sand is a good example of silicon dioxide. And these are considered to be network atomic solids. Now, atomic solids and molecular solids are going to have extremely different properties. Molecular solids like methane, this would be solid methane, or sucrose, or ice, for example, is also a molecular solid. basically your solid is dependent on an attraction of one molecule to another molecule. So this molecular solid will only be as strong as the attraction is between the two molecules. Well, that's not a bond. That's not an ionic bond, and that's not a covalent bond. That's not a bond when you're talking about the attraction between two molecules. It's something called an intermolecular force, a force between two molecules, right? And that's not as strong as a bond. And so as a result, molecular solids are going to have very low melting points and boiling points, like we see with water, for example. In order to get water to melt, you just have to go to 0 degrees Celsius, right? That's not very high. That's not like the volcano we're talking about that it's going to take to melt an ionic solid. They're also going to tend to be hard and brittle. Again, those attractions are going to be fairly easy to disrupt. So you can shatter rock candy, you can shatter ice. They're going to be hard and brittle. An atomic solid, on the other hand, the attraction between the atoms at each point in its lattice, that is a covalent bond. And so these are going to have very, very strong attractive forces between them. So it's going to lead to high melting point and boiling point. They're also going to tend to be hard, brittle. Silicon dioxide is in this group. Diamonds are in this group. Graphite is in this group. They are some of the hardest material that we can find on Earth, right? We use diamonds to cut everything else because it's so extremely hard. And so, as you can see, covalent bonds are not quite as easy to categorize in terms of properties because there's a couple different structures that can form that involve covalent bonds. We haven't actually talked about the group 8 solids, but these are the solids that can be formed from a noble gas. They're super weird. They're super unstable. They're really hard to get to form. So we're not even going to talk about properties of those because they're so unusual. If you're studying group 8 solids, you're probably getting your doctorate in noble gas materials, right? There's really not too many other people who are studying the properties of the noble gas solids because noble gas solids just don't form. Okay, so all of this to say, what are the driving properties of things that are covalently bonded? Well, they're a little bit all over the board. They can have high melting points like diamonds, or they can have low melting points like carbon dioxide. They can be extremely hard like sand, silicon dioxide, or they can be very easily shattered like sucrose. They can tend to exist as a gas like methane and oxygen and carbon dioxide and fluorine, or they can be solids like silicon dioxide, diamonds, graphites. Some of them are even liquids like bromine and iodine. Bromine tends to be a liquid at room temperature. Iodine tends to be a volatile solid. Volatile means that it turns into a gas very easily. So if you have solid iodine, you actually have to keep it sealed. Otherwise, you'll get this creepy purple vapor that's coming off of it. So covalently bonded things tend to form a more diverse array of structures. And so they're going to get a more diverse array of characteristics as well, which we've talked about before, but now you understand why. Okay, so that's kind of your overview on covalent compounds. Next, we're going to talk about a little bit more about what that bonding looks like in covalent compounds. Okay, so let me know what questions you have. I will see you in class.